Alright, now we are going to discuss phenols, a very important class, phenols. So, in general, phenols क्या होते हैं? What are phenols? Phenols are the compounds in which the hydroxyl group is directly attached to a benzene ring, right? So, this is phenol, and this compound is also phenol, but we can name it as 2-methyl phenol, right? And similarly this can be your 3-methyl phenol, right? And this can be 4-methyl phenol. And there is a common name of this compound also, और वो common name है cresol. And as we have learned in +1 class, this compound in which a benzene ring has a substitution of methyl and hydroxyl group, जिसमें दोनों ग्रुप्स हैं, उन्हें हम क्रीसोल बोलेंगे. और हाइड्रोक्सिल ग्रुप के कंपैरेटिवली ये उसके एडजेसेंट पोजीशन पर है, तो इसे हम बोलेंगे ऑर्थोक्रीसोल. इसके केस के लिए हम बोलेंगे मेटाक्रीसोल, और इसके केस के लिए हम बोलेंगे पैराक्रीसोल. ऑलराइट. एंड अगर बेंजीन रिंग में अगर डबल हाइड्रोक्सिल ग्रुप की सब्स्टिट्यूशन है, राइट, तो इनके जो आईयूपैक नेम्स हैं वो फिनोल से नहीं मैचअप होंगे, तो उसके लिए नेम होगा हमारे पास बेंजीन, राइट, बिकॉज इट इज़ बेंजीन. देन बेंजीन 1,2 diol, and we can number this carbon as 1, this as 2, or you can number it as 1 or this as 2, right? So this is benzene 1,2 diol. So this is benzene 1,3 diol and benzene 1,4 diol. I hope it's very easy to understand. And the common names which are very famous for these three compound is, this is called catchol or catol, catol. Then this is resorcinol, and this is known as quinol, right? Quinol. So these were just a simple nomenclature of phenols. And now we have physical properties of phenols. As you can see that benzene and chlorobenzene, bromobenzene and phenol, if we compare all of these compounds, means benzene containing compounds, then what we observe that the boiling point rises. Benzene has lower boiling point than chlorobenzene, which has further lower boiling point than bromobenzene, and phenol has the highest boiling point. And what reason we can expect for this? And the reason is simply same as that for alcohols, and that reason is known as hydrogen bonding, right? So in phenols, because of intermolecular hydrogen bonding, right, the boiling point of phenols is higher than its other molecules, which are like chlorobenzenes and bromobenzenes. All right. Now let us go for preparation of phenols. Phenols can be prepared mainly from these four set of compounds, right? First is from the benzene sulfonic acid. Now here I have extended the reaction from benzene. When we react benzene with oleum, right, and this is oleum H2SO4 plus sulfur trioxide, this is called oleum at 353 Kelvin. When you react benzene with oleum, then we get benzene sulfonic acid, SO3H. This is still acid. This is benzene sulfonic acid, and you can write the name benzene sulfonic acid, right? And when this acid, it reacts with a base, a very common base, sodium hydroxide, then definitely what reaction we are going to expect? This hydrogen will be eliminated with this hydroxyl group, and we will get this compound. This is known as sodium benzene sulfonate. Then this compound is basically treated with sodium hydroxide. Basically you can combine the two processes and you have to melt them, right? You have not to add sodium hydroxide solution, but you have to add sodium hydroxide in liquid form, or we can say the reaction will take place at very high temperature, right? And this temperature is around 573 Kelvin. This will give you sodium phenoxide. This compound is called sodium phenoxide, and this is now a salt, sodium phenoxide. This is a salt, and what we get if we treat this salt with hydrochloric acid, HCl aqueous, definitely you will get weak acid, which is a phenol, right? Along with that you will get sodium chloride. So this was the first method of preparation. Now let us go for the second method of preparation, and this method is from aniline, and this compound is known as aniline. When aniline is treated with sodium nitrite and HCl at 5 degrees Celsius, right? Now we have to understand why we have added this. The purpose of sodium nitrite and HCl is to generate a weak acid, which is nitrous acid along with NaCl. So this acid is basically not available, rather it is always prepared when required, right? So with this, what we are getting, we will get this compound, and this nitrogen will have positive formal charge, and this compound is known as benzene di means 2 diazonium chloride. Okay, di means 2, azo stands for nitrogen, 2 nitrogen, and em stands for positive, right? And this benzene diazonium chloride, when it is treated with just water, warm, right, then we are getting phenol, right? Along with phenol you will get HCl, which is a gas, plus nitrogen, again a gas. So you can remember this reaction very simply in this format: HCl goes and nitrogen goes. So keep in mind, whenever diazonium substances are going to react and this group is going to eliminate, there will be liberation of nitrogen. नाइट्रोजन हमेशा रिलीज होगी, राइट? थर्ड मेथड है हमारे पास फ्रॉम क्लोरोबेंजीन, और थर्ड मेथड को एज इट इज़ बैक एक्सरसाइज में क्वेश्चन नंबर 11.10 में पूछा गया है. ऑलराइट, सो हाउ वी आर गोइंग टू perform this reaction. So from chlorobenzene you have to remove this bond, right? Finally we are going to have phenol. So this bond, the bond between the carbon of benzene and chlorine will break, right? And for this you need sodium hydroxide, 623 Kelvin temperature, along with 300 atmospheric pressure. This is called drastic condition, right? The same condition was applied at this point also. Whenever you have to break the bond directly linked to benzene, you have to make the drastic conditions. So what we are having now, we have sodium phenoxide, the same compound. And now how we are going to get this phenol? Again same case, hydrochloric acid. Keep in mind you have to write aqueous, means ये hydrochloric acid होगा. Alright. So that was from chlorobenzene. Finally we have cumene, and this compound is called cumene. So from cumene, how we can get this phenol? We have phenol. So क्यूमीन क्या है? एक प्रोपेन के मिडिल कार्बन पे एक बेंजीन रिंग अटैच करना, प्रोपेन के मिडिल कार्बन पे बेंजीन रिंग अटैच करना क्यूमीन कहलाता है, राइट? और हम इस क्यूमीन की सिंपल एरियल ऑक्सीजन से रिएक्शन करते हैं, तो इस रिएक्शन के बाद जो हमें कंपाउंड मिलता है वो ये मिलता है OOH, यानी कि इस कार्बन से जो कार्बन प्रोपेन का मिडिल कार्बन है उस पे एक ये परऑक्सिल ग्रुप लग जाएगा, राइट? और इसका नाम होगा क्यूमीन हाइड्रोपरऑक्साइड। फाइनली आप इसमें डाइल्यूट एसिड ऐड करेंगे, हाइड्रोक्लोरिक एसिड यू कैन ऐड, और इसके बाद आपके पास जो कंपाउंड बनेगा वो फिनोल बनेगा, और फिनोल के साथ में आपके पास आएगा एसीटोन। तो ये जो कार्बन आपके पास होगा, ये वाला कार्बन एज एसीटोन निकल जाएगा, और ये जो हाइड्रोक्सिल ग्रुप है वो इससे अटैच होगा। दैट वाज ऑल अबाउट द प्रिपरेशन ऑफ फिनोल्स। क्यूमीन की प्रिपरेशन आपके पास बैक एक्सरसाइज में एज 11.9 क्वेश्चन दे रखा है, दैट इज स्ट्रेट फॉरवर्ड क्वेश्चन। ऑल राइट, and we are going to discuss the chemical properties of phenols, and here is a very simple structure of phenol, and we can reveal the chemical properties from this structure. phenols की chemical properties को हम mainly 3 categories में classify कर सकते हैं. This bond cleavage, A cleavage, will give the acidic properties of phenol. ऑलराइट, मीन्स कि कुछ ऐसी रिएक्शंस हैं जिनमें फिनोल एक एसिड की तरह से बिहेव करेगा, दोज आर कॉल्ड द एसिडिक प्रॉपर्टीज ऑफ फिनोल, एंड देयर विल बी सम रिएक्शन इन विच द बेंजीन रिंग ओनली इज इन्वॉल्व्ड, राइट? सो दिस इज वन कैटेगरी, दिस इज द सेकेंड कैटेगरी, वी कैन कॉल इट बी कैटेगरी, राइट? एंड देन there will be a third category of reaction in which OH group is involved along with benzene ring, just like alcohols, and that combined we can group it as C category. And there can be a one fourth category also in which only OH group is involved, only OH group is involved, that can be called as D category, but we are going to study only main 3 categories, right? And the D category will be oxidation reaction. So A category will be acidic properties, right? B category will be electrophilic substitution reactions, right? And these 2 compound states will give you some very interesting reactions, right? And the D category will be oxidation reactions, right? For exam purposes, for exam point of view, A category and C category is the most important, right? So now we will start with the first chemical property, that is A category, means acidic chemical properties of phenols. And that acidic nature of phenols can also be compared with ethanol. We have learned in alcohol lecture that alcohols, they do not react with sodium hydroxide, so it's very simple, right? And the phenols, they can react with sodium hydroxide to give you phenoxide salt, sodium phenoxide salt plus water. Now you might be thinking that since the pKa of ethanol was 16 and that of water was 14, and now what we are going to expect from phenols, the pKa of phenol is basically 10.0. This is given in your NCERT book, and at the back end exercises it is given that give two reactions, right? Give two reactions so that to show the acidic nature of phenol and compare the acidic nature of phenol with that of ethanol. So what we compare, what we are going to draw the conclusion from these two reactions. The conclusion is very simple: phenols are more acidic than alcohols. And then we have to reason it out also why phenols are more acidic than alcohols. So let us understand the reason first. So here we can understand that when a base reacts with acid and we get conjugate acid and base, the reaction is very simple. These lone pair, they are going to land on hydrogen and these bond pair will land on oxygen. So the substance which was earlier base, जो पहले base था, that substance after gaining hydrogen will become its conjugate acid. The difference between base and its conjugate acid is that a conjugate acid has one hydrogen more than its base, and an acid and its conjugate base has a difference that conjugate base has one hydrogen short than its acid. So very simple concept. If the base is very strong as compared to acid, then it will show its character, right? A strong conjugate base will be converted to a weak conjugate acid, and a weak conjugate acid will be converted to strong conjugate base, right? And this group R, this R can be a benzene ring also, right? And when it becomes benzene ring, then we can understand now that this is now a phenol, while this was can be treated as alcohol because R generally indicates the alkyl group, and I have just replaced this alkyl group with this benzene ring so that we can understand that the same concept will be applied for phenols also, that this base attacks and what we get BH along with this anion, right? And this anion is known as phenoxide ion, right? For alcohol, this ion is known as alkoxide ion. Now the acidic nature of phenols can be understood very simply if we just first understand the basic process of showing the acidic nature, right? So now suppose I have phenol, right? This is phenol, and this substance now act as acid. Shorter arrow shows that they are not very stronger acid, but they are stronger than water. Why? Because the pKa value is 10, which is less than water. So when this substance is going to act as an acid, you will get phenoxide ion along with hydrone, alright. Now if we are going to add water, then this H2O will appear here and this will become hydronium ion. So phenols behave as acid in the presence of water. Alcohols do not behave as acid in the presence of water. Okay. Now here is the problem. The problem is that we can understand this is a negatively charged species and here is the positively charged species. Now they can react together to give you back the phenol and water. So if they react back, that means this substance is not acting as an acid. While on the other hand, if we understand that they do not combine, if they do not combine, that means they will remain as two different separate entities. That means this substance has shown successfully its acidic character because it is not combining with its own hydronium ion generated. Well, so phenol has the same characteristic, means this phenoxide ion is not going to bind with the hydronium ion again, right? Now the question is why? Because there are opposite charges, why? And the answer to this question is very simple, right? We can understand it simply with the help of some resonating structures. For example, in phenoxide, now oxygen contains 3 lone pairs, right? And then again the same picture, that these lone pair can be overlapped with this benzene ring, right? First of all, we should understand why and how this overlapping takes place. That we will learn later on. But now, this lone pair will be combining with this carbon. Okay, focus on this tip, and this pi bond will shift to this carbon. Focus that I have touched this pi bond and then I have touched this corner also, so that we can understand that these 2 electrons will be shifted to this. And now what we are going to have the situation next, when they shift, this bond will remain as such, this bond will also remain as such, but these 2 electrons will be on this carbon and we can show their 2 dots. Keep in mind that the total number of dots were 6, or there were 3 pair of electrons and there are still 3. And with this electron pair there will be 1 additional bond, right? And then after this situation, what we are going to observe, that this electron is going to make bond with this carbon, and again this pi will be shifted to this carbon, and we will show this with this picture. Here is the bond, and now the 2 dots shifted to this part, right? And this process will be repeated one more time, alright? And then you will get this bond as such, this bond, new bond, right? And here is the 2 dots, right? And now finally these 2 dots will bond with this carbon, and this bond will be taken back by the oxygen, and thereby you will get all the 3 pair of electrons back, and the bonds will be again within the benzene ring. Now the point which we are going to understand is that the enthalpy of resonance for benzene is approximately 30 kilocalories per mole, and this is approximately 150 kilojoule per mole. So why I have given this data to you? Because it is required to understand that why we need these set of 3 pi bonds within the ring, because the benzene ring is highly stabilized by the resonance. Now these structures show that the negative charge or the negative electron density on oxygen is now dispersed on complete molecule. For example, it was earlier on oxygen, now it is at the ortho position, next at the para position, back to ortho position and back to oxygen, right? So out of these 5 structures, if we notice these 5 structures, out of these 5 structures only 2 structures have the negative charge on oxygen, that means 2 by 5th, right? And these 2 by 5th times the 100 will give you 40%, right? That means because of the resonance, the negative electron charge density is 60% distributed on the benzene ring and it remains only 40% on the oxygen. Okay, that means the picture which we were earlier thinking that there is a negative charge is now little bit changed. Now we can say there is a 40% of charge, and therefore the combination possibilities of this phenoxide ion and the hydronium ion will definitely decrease, therefore they will remain separate, and it means that phenols have acted as good acids. On the other hand, when you have ethoxide, for example this is ethoxide, methoxide, propoxide, general alkoxide, then these alkoxides do not have resonating structures like phenols, right? So therefore the electron charge density on oxygen is not likely to disperse, but if we have alkyl groups, then because of the plus inductive effect, these groups will tend to increase the negative charge more on oxygen, right? So in phenols we have noticed that there was dispersal of negative charge and the charge density on oxygen was remained only 40%, while in case of alkoxides the charge density will not remain 100%, rather more than 100% because of these alkyl groups and their positive inductive effects. So definitely they will combine faster with hydronium ion and give back alcohol. So therefore alcohols will be weaker acid as compared to phenols. Now we can make the phenols little bit more acidic if we make some substitutions. As we know that in these 5 structures the electron density is on ortho, para and ortho. So if we have some functional groups, right, which can withdraw these electron densities, then that group can help in reducing the electron density overall furthermore. Thereby they can make the phenols much better acids when they are substituted. For example, we have this simple phenol, right, and when we combine this substance or we substitute this substance with another functional group like nitro, and remember that this functional group is electron withdrawing functional group, and what is the effect of that functional group? Well, the effect is very simple. First thing is that we should know that there were negative deltas at ortho positions and at para position, right? At ortho positions and at para position. Now, because oxygen will withdraw these pi electrons towards itself, so nitrogen will have shorter of electron. Nitrogen per electron density reduce जाएगी. As a result of that, these pi bonds will shift towards nitrogen, right? And we can represent them in pictures like this. And in this picture, we observe that this carbon is now become positive and this oxygen is negative. Overall they are neutral. Now what does it mean? It means that this carbon is now become more electronegative, and then this is going to pull this pi bond towards itself, right? So again the picture will change, and this time after shifting of this pi bond, this positively charged density is now shifted to the carbon which is directly bonded to hydroxyl group, right? And this is good. Why? Because when these substances, when they will act as acid, when they are going to act as an acid, under that situation, when you have positive charge, then therefore the electron density from oxygen can be withdrawn towards the ring. And so if we notice the whole picture, right, if we notice the whole picture of phenol or phenoxide ion with this simple picture, we can understand the picture very simply, right? For example, what we are going to observe that the electron density from oxygen has flown down towards oxygen or towards this nitro group. Such type of groups, they are called the electron withdrawing groups, right? But there is a big problem, right? And the problem is that of position of such groups, right? Now since nitro group when attached directly to para position or ortho position, means the position where there were increased electron density in case of phenoxide resonating structures, only then they are very effective. But when they are attached at some meta position, not at ortho, not at para, but at meta, then what will happen? Now see, these bonds will shift towards oxygen. Very simply, nitrogen will get little bit positive, and then these electron will shift towards nitrogen, and this carbon will little bit positive, and then this bond will shift to this carbon, and then this carbon will reverse positive. That means electron density has been shifted from this point on to this, right? But the problem is at this region, right? If you look at this region, when the nitro group was attached to the para position, then the electron density was reduced at the carbon that was attached to oxygen directly, while when nitro is attached to the benzene ring at para position, then the electron density of the carbon which is attached to hydroxyl group is not reduced to a greater extent, but reduced to a very lesser extent. Reduced, still reduced, not like this. So if I am going to write here ortho nitrophenol, right? And then its para isomer, and then its meta isomer. Then out of these three, the meta isomer will have pKa value 8.3, right? And the para isomer will have 7.1, and the ortho isomer will have 7.2 pK value. And we know that higher the value of pKa, lower is the acidic character. That means phenols, in case of phenols, meta-nitrophenols will be less acidic than ortho, and ortho will be less acidic than para-nitrophenol, right? Now suppose if we have phenol but substituted with some other groups. For example, these groups were electron donating groups, and suppose the phenols are substituted with some electron donating group like methoxyphenol, right? So what do you observe, that if I have phenol substituted at ortho position with a nitro group, and we have phenol substituted at ortho position by methoxy group, then out of these two, which one you think will be more acidic? And the answer to the question is very simple. Because nitro group is electron withdrawing group, like electron withdrawing group, and this is electron donating group, right? So this group will not going to reduce the electron density, rather it is going to increase the electron density, thereby making the methoxyphenols lesser acidic than nitrophenols. And for this explanation you can go for your exercise number question number 11.15 and you can solve it. And similarly, related to ortho and para-nitrophenol, there is one more interesting fact that we have studied in +1 standard. If this is phenol and this is now orthonitrophenol, right? And then we can draw one more molecule of orthonitrophenol representing this one. And if we have this was para-nitrophenol, and if we have orthonitrophenol like this one, then what we observe, that in case of orthonitrophenol, this hydrogen which was thought to be showing the acidic character is now bonded through hydrogen bonding with this oxygen, and such type of hydrogen bondings are called the intramolecular hydrogen bondings. In case of nitrophenol, we can see that there is intramolecular hydrogen bonding. So out of nitrophenol and out of para-nitrophenol and orthonitrophenol liquids, which one will have higher boiling point? Well, the substance in which the molecules are bonded together will have higher boiling point in case of para-nitrophenol, and in orthonitrophenol the molecules, they are not bonded together, but the molecule is bonded within itself. Right, so out of these two, para-nitrophenol will have higher boiling point, orthonitrophenol will be having lower boiling point, or this will be more volatile than this one. Related to this fact, you can solve your exercise number question 11.8. Alright, and we can compare the acidic character of cresols also. For example, if we have orthocresol, paracresol and metacresol, then orthocresol has 10.2 pKa and para will have 10.2 2 pKa, while meta will have 10.1 pKa, right? So we have to think that phenol has pKa 10. That means cresols, they are less acidic than phenols, and nitrophenols, they are more acidic than phenols, right? So now we can solve one of the question related to this acidic character, which is very simple and easy. Out of these three compounds, this is 3-nitrophenol, this is 3,5-dinitrophenol, and this is 2,4,6-trinitrophenol. Out of these three, which one is most acidic, right? And the answer is this one. We know that the electron withdrawing groups, they increase the acidic nature, and therefore as they increase, they also increase the acidic nature, right? So that was all about the first chemical property of phenol, that was the reaction with bases. And one more reaction you can add to this: if you have phenol and you react with sodium, you get sodium phenoxide along with hydrogen as a gas, all right.